Hello everyone and welcome back. Before we begin, I would like to present two definitions for the course. These are words that you know already. However, again, how they're used specifically in the physics classroom is important to know. The first word is speed, a word used to describe how fast an object is moving. This is a word that we use in our everyday language and we use it correctly. Something can have a fast or a high speed or a slow or low speed. So say something is fast, something is slow. How we use this is perfectly fine. Now, the word we don't typically use in everyday language is velocity. Velocity is a little more specific. Velocity is taking the speed, but also including the specific direction the object is moving in. Speed in a given direction. This direction can be north, south, east, west, up, down, left, or right, or if you're working in a single axis, positive direction and negative direction. What you use depends on your point of view for the problem. For the signs, typically positive direction will mean to the right, negative direction mean to the left, or if you're working on the vertical axis, positive direction is upward and negative direction is downward. We're going to start by analyzing the motion of this man moving from right to left. As you can see, he's starting at the positive 10 meter mark. He's going to move to the negative 10 meter mark. And there's going to be a red arrow that represents his velocity as he does this. Here we go. So, taking into consideration the motion you just witnessed, we're going to create two graphs that represent what you just saw. And I'm not even going to use numbers because that is not the point of this video. The point of this video is to really get you comfortable with the shapes involved with these graphs and how they work in general. The two most common graphs you will encounter in a physics course is a position versus time graph, which I have on the left, and a velocity versus time graph, which I have on the right. So the motion man first started at a positive position. He went through the origin point, which was 0 meters, and ended up at a negative position that was equally distant. So we started at the positive 10 meter mark, ended up at the negative 10 meter mark, which means, and if this is the 4 seconds, he ended up here. Now, as he went from right to left, there was no change in his velocity, which means this graph is a straight line from the first point to the last. Now, whenever you create or you are given a graph, there are always two things about the graph that are important to know. The first is, what does the slope of the graph mean? The easiest way to check that is simply to use, probably was one of the first things you learned about the slope to begin with, is rise over run. I'm going to take the rise over run, and I'm just going to do it with the units I have here. So the rise on the y-axis is meters, and the run on the x-axis is seconds. I do that, and I have the unit meters per second. Well, this is the unit for a speed or a velocity. Looking at the slope of my line, the slope of my line is negative, which means this not only has a negative velocity, it is a constant negative velocity, which also was a check to make sure that your graph is correct. We saw the man move from right to left at a constant velocity. This slope goes from positive to negative, and it is a constant slope, so does a constant velocity. The second thing about a graph I'm going to bring up when we get to the velocity versus time graph. Now, speaking of which, here's your velocity. So the velocity we witnessed was to the left, so it's negative. So it's starting down here, and it was constant. Now, this is not going to change because the y-axis represents velocity itself. So the velocity was negative and stayed constant for the entire time period. Now, I said there are two things about the graph you should check. The first is, what does the slope mean? And the slope is rise or run. Well, for position versus time, rise over run is meters per second, which is velocity. For velocity versus time, I get meters per second over seconds, which is a rate of change of velocity. This actually has another name, which I'm not going to mention right now because it is so important that it's going to deserve and have its own video. However, the other thing about a graph you may want to check is the area under the curve. And in this case, that would be this. Now, the simplest way to check if the area under the curve represents anything for a graph is if this is area and this is the rise, this would be meters per second because it's the y-axis, and this is the run, and this is seconds because the x-axis. I want to think of this as a rectangle. So instead of rise over run, it's going to be height times base. And height times base will give me meters per second times seconds. Well, if these two cancel, I get meters. And that's a clue that this area here on the velocity versus time graph gets you displacement in meters. If I try this for the position versus time graph, however, I do rise times run or height times base, I'll get meters times seconds. And meters times seconds is no known unit here. So it isn't very useful for position versus time graph, but can be very useful for velocity versus time graph. So to recap, my position versus time graph has a linear shape. The slope does not change because the slope represents velocity, which can also be called the rate of change of position. And that is not changing. So this is a constant velocity. For a velocity versus time graph, the slope is 0 because there is no change in velocity. The velocity remains constant. It is negative. Remember correctly, it was negative 5 meters per second, in fact. It is negative, and it remains constant negative the entire time. Now, let's observe another type of motion. Let's go back to our motion man. This time he is going to start from rest. He's going to move from left to right, and he is going to increase velocity at a constant rate. And again, there is going to be a red arrow representing his velocity. Okay, now that we've seen another example of motion, let's take a look at what happened here. So in this one, our motion man began in a negative position. It's actually negative 10 meters. This is 0. And again, ended up at a positive, at another side, at positive 10 meters. So without putting anything else yet, I'm simply going to add the first point and last point here. At 0 seconds, he was here at the negative 10 meter mark. At the end of our experiment, he was at the positive 10 meter mark. So I absolutely know this, so these 2 points are definitely going to be in my data. Now, let's talk about what the shape of this graph will look like. If I start here and go directly to the endpoint, well, what does that mean? That would mean that he went from the negative 10 meter mark to positive 10 meter mark at a constant velocity. But just by watching what he did, we know he didn't do that. And we literally saw the arrow grow bigger that represented velocity, so the velocity has to increase. This right now states the velocity is constant, so this does not represent what the man did. You can actually piece together what this graph will look like by doing this. You can actually think about it in small pieces. At the very beginning, he wasn't moving. Non-moving on a position versus time graph means it would be flat. In other words, if he never moved, he would stay at the negative 10 meter mark the entire time. Now for the next little mark, I'm going to do another little line that represents it going a little faster. So if the slope of the line in the position versus time graph represents velocity, a little faster would mean a little larger, higher slope. Then he went a little faster than that. That's a little higher slope. Then he went a little faster, and 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 a little faster. So if I piece it together, then I have a slope that is steadily increasing and I get this curve. So the actual shape would look something like this. This represents our man starting from the negative 10 meter mark, moving to the positive 10 meter mark, and increasing his velocity while doing so, because the slope of the line represents velocity and it's the actual slope that is increasing, as well as the position changing. So what would this look like in a velocity versus time graph? Well, in a velocity versus time graph, his initial velocity was 0. So my starting point is going to be right here. At the end, so I'm looking at this section right here, his velocity is positive. So at the end of the time limit, his velocity is going to end up somewhere up here. Now, there's one piece that is actually difficult to tell in the video, so I'm just going to hand it out. The velocity for that man increased at a constant rate. Now, if we remember for position versus time graph, the slope was meters over seconds, which is velocity, and for a velocity versus time graph, meters over seconds is rate of change of velocity, how quickly the velocity changes. But as I just said, the velocity changed at a constant rate, which means this is going to be a straight line. The velocity is increasing and is increasing at a constant rate. So going from 0 meters a second to whatever his final velocity is was done in even increments. Just a side note, in Physics AP1 or any first year physics course, this is typically the only kind of change in velocity you will be dealing with. Unless it's a theoretical question, all the changes in velocity in AP1 physics class are going to be constant changes in velocity. So a shortcut for that is, if you are creating a velocity versus time graph in a first year physics course, it most likely will not be curved, because having this graph be curved is very rare. Higher level physics, you see it more often, but for your first physics course, it's actually very rare to see that. All right, now I have one challenge for you. For this challenge, we're going to use the exact same motion for the graphs we just created. Here we go. So after watching the video again, let's actually start putting in some more values. The starting position was -10. He went to +10. I already have those in. The time it took was 7.2 seconds. I'm going to put that here as well, 7.2 seconds. So the challenge is, can you find the velocity of the man when he hit the wall on the right-hand side? For these graphs, what I'm asking for is, what is the velocity here? Now, pause the video, see if you can find it, then start it up again. Okay, before we begin, there's one thing I would like to mention, and that is, if you ended up with an answer of 2.77 meters per second, you are wrong. Now, the whole point of me bringing up this question is to show you why, and to bring up a few important things in the course. Let's analyze the situation and actually list some givens. Begins at the -10 meter mark, ends at the +10 meter mark, so I have a displacement of positive 20 meters. I have time of 7.2 seconds. Now, here is the common mistake. Velocity, since velocity has to have the units meters per second, take displacement over time, and I will get 20 meters over 7.2 seconds, which gives me the 2.77 repeating meters per second. This answer is incorrect. And it's incorrect because it does not answer the question that was being asked. This is a velocity. It is actually a useful velocity. However, it is not the velocity that was asked for. So before we continue, let's actually answer the question, what velocity is this? Because it brings up something else much more important. In physics, there is never just v. There should be a subscript here. And the question is, which subscript is it? To give you an example, I didn't finish my givens list. We definitely have a velocity initial. The velocity initial here is 0 meters per second. What I have asked for is velocity final. That is represented here, where the 0 is velocity initial. So the question is, what is the final velocity of the person when he hits the wall on the right-hand side? Let's take a step back and take a look at what you have found. This velocity takes the entire displacement over the entire time period. This isn't the initial velocity because we know it's 0. It's not the final velocity because whatever that is the fastest he is actually going. What you have found here is the average velocity. And this is actually going to be our first physics equation for the course. Velocity average is displacement over time. Since displacement has a direction, so does velocity. Displacement can be right, left, velocity can be right, left, displacement can be positive, negative, velocity can be positive, negative. Now, since we have the average velocity, which actually is useful, where does it belong on my graph? Well, since the rate of change of velocity is constant, the average is going to be dead center, and that's going to be right here on the y-axis. So your velocity is not on the line here. This is the middle of your graph. Your velocity is the y-axis. So your average velocity is here. And if the rate of change is constant, that means your average velocity is dead center. It works very similar to test scores. If, Newton forbid, you got a 0 on a test, and you took a second test, and after those 2 tests, your average is a 40, what did you get on the second test? Well, if your first test was 0 and your average is a 40, and they were evenly distributed, then the second test, you received an 80. So in this case, it would be double whatever the average is, which means final velocity would end up being 5.55, repeating, meters per second. And that would be this value right here. So a few key points here. Velocity always has a subscript. Velocity initial, velocity final, velocity average. You could also have velocity constant, which is an average velocity. So if our motion man in the beginning went negative 5 meters a second the entire time, that is both a constant velocity and an average velocity. So displacement over time gets you velocity average. It does not get you velocity final. We're going to get into a little more discussion on breaking this graph down a little later. But for now, thank you for joining me. I hope this has helped you out. Have a good day. This is Mr. M signing off.